Hello everyone, my name is Andrew Draguch. I'm the first author on this article and I'm from the University of Waterloo, which is just outside of Toronto in Canada. It's with great pleasure that I'm providing this visual abstract for the Fracture and Structural Integrity Journal article. This particular article is detailing the nuances of an improvement of fatigue properties of magnesium alloys achieved through forging, but it's part of a larger project where we actually designed, analyzed, optimized, and manufactured automotive suspension components from magnesium alloy for vehicle lightweighting initiatives, as you can see here on the bottom left. I'd like to take this time to acknowledge the support of the funding agencies and industrial partners who made this work possible. Axial monotonic and low control fatigue tests were performed to investigate the influence of forging at various temperatures and different deformation rates on both the microstructural and mechanical behavior of extruded AZ31B magnesium alloy. A video as well as a simulation of the forging process are shown here, with equivalent strain being shown in the contour plot of this elastoplastic simulation. The obtained microstructural analysis showed that the extruded AZ31B magnesium alloy possesses a bimodal grain structure with strong basal texture. In contrast, once forged, the material reoriented its grains and had a refined grain structure with a modified texture, such that the C-axis reoriented itself to be coincident with the direction of forging, as can be seen here. You can also see that the initial crystallographic texture, which is axisymmetric, illustrated by this schematic, then evolves to this planar basal texture as shown here. Both the yield and ultimate strengths, as well as the ductility of the material, were improved due to forging, with lower temperatures and higher forging rates being favorable for higher strengths and higher ductilities. In compression, twinning is very active, as can be seen in the stress strain plot illustrated on the right. This results in a large disparity in the response between tension and compression, known as yield asymmetry, which is a phenomenon that is very common in most form of magnesium alloys, and the cause is linked to the hexagonal close-packed crystal structure. Taking a typical dog bone sample as shown here and deforming it in tension, basal slip is activated and the material hardens monotonically. However, deform the same sample in compression and basal slip is no longer favorable, and the crystal will effectively twin to accommodate the compressive deformation as illustrated by this animation on the bottom right. Forging improved the fatigue life via a combination of grain refinement and texture modification, resulting in improved strength and ductility. Evidence of this is shown in these SN curves here, where a balance of strength and microstructural homogeneity favor longer lives. Thus, the most favorable forging conditions are those which were investigated of all the ones here was 3.9 millimeters per minute and 400 degrees Celsius. The fracture surfaces of all samples were characterized by a terrace-like faceted morphology with an intergranular fracture path as in the as-extruded condition, whereas the forged conditions exhibited a much more dimple-like fracture surface and transgranular fracture path indicative of more plasticity, as can be seen here.